Okay, so welcome to the Pacific Category Theory Seminar. Today's speaker is Yuki Imamura at RIMS, Kyoto University, and he's going to tell us about a formal category theoretic approach to the homotopy theory of DG categories. Please start.
Okay, let me start. Thank you very much for the introduction. I would also like to thank the organizers for giving me the opportunity to speak at this seminar. And thank you all for coming today. Today, I will talk about the topic displayed on this slide, a formal category theoretic approach to the homotopy theory of the G categories. Before I begin, I would like to ask you a small favor. Since I'm not very good at understanding spoken English, I would appreciate it if you could speak slowly and clearly when asking questions or making comments. Of course, all questions and comments are welcome. Okay, let me begin the talk. Oh, okay. Today's talk is based on my archive preprint with the same title. Here is the outline of this talk. First, I will briefly recall the G categories and their homotopy theory. Second, I will introduce formal category theory. Then, in the third part, I will explain an approach to the homotopy theory of the G categories using formal category theory. More precisely, I will construct a plural equivalent in the sense of Richard Wood, which captures the homotopy theory. Finally, I will discuss some properties and make a few remarks. So let me begin by recalling the G categories. Throughout the talk, everything is over fixed base field K for simplicity. A differential graded category, or the G category for short, is an enriched category over the monoidal category of complexes over K. Precisely, this means that we are given a collection of objects of A, and for any two objects, A and B, the home is not just a set, but it is a complex of K modules. We have composition maps, which are homomorphisms of complexes and identities given by degree zero cycles. These satisfy the usual associativity and unit actions. Now, let me give some examples of DG categories. A typical example is the DG category of complexes. The objects are complexes of K modules, and the home object between two complexes is given by the standard home complex. That is, the degree n term is given by this module, and the differential is given by this formula. This DG category will be denoted by CDGK in this talk. Other examples include pre-additive category, since their home abelian groups can be regarded as complexes concentrated in degree zero. Also, DG algebra is nothing but a DG category with a single object. A DG category is an enriched category, but it also has a homotopical aspect. From a DG category A, we obtain an ordinary category Z0A by taking 0 cycles of each home complexes, like this. This is the underlying category of A. If we take zeroth cohomology instead, we obtain another category, H0A, which is called the homotopy category of A. We can also consider DG modules over A, that is, DG precedes on A. We write CA for the category of DG modules over A. If we localize this category at Kesi isomorphisms, we obtain the derived category of A, denoted by dA. This is a triangulated category. There is a canonical free faithful factor from H0A into dA given by this Yoneda-like assignment. This embedding will play an important role later. DG categories play a central role in algebraic geometry and representation theory because they provide enhancements of triangulated categories. A triangulated category is an additive category equipped with a shift factor and a collection of distinguished triangles satisfying some axioms. In particular, every morphism admits a cone and a cocone, which is like a mapping cone of a morphism, though the construction is not functorial. The G category A is called pretriangulated category, pretriangulated. If its homotopy category, H0A, is closed under shifts and cones inside the derived category, dA, where the embedding I just mentioned. This. In that case, the homotopy category, H0A, is a triangulated subcategory of the derived category, dA. So pre-triangulated DG categories can be regarded as enhanced triangulated categories. For this reason, they are widely used in the study of triangulated categories. DG categories also carry a homotopical structure as follows. First, we call a DG factor F as a Kesi equivalence if the following two conditions hold. For every object A and A prime, the induced homomorphism on home complexes if A prime is a Kesi isomorphism, and the induced factor on homotopy categories H0F is essentially surjective. This is a homotopical analog of an equivalence of categories. The category of small dg categories admits a model category structure in which the weak equivalencies are precisely the KSI equivalencies. Using this structure, we obtain the localization of the G-cat that at KSI equivalencies, and uh, we write HODG-cat for it, for the localization. And we call it the homotopy category of the G categories. Next, I move to formal category theory. Formal category theory is an approach that studies category theory itself from a two-categorical setting. In classical homological algebra, homological arguments in module categories are abstracted to abelian categories. Similarly, formal category theory formalizes categorical arguments that are usually carried out inside the two category of categories. There, there are several frameworks for formal category theory. Here, we consider the notion of a plural equipment introduced by Wood. Like other frameworks, using the structure of a plural equipment, we can develop category theory in a very abstract way. In particular, we can give a unified definition of limits. Now let me see the definition of a plural equipment. Let K be a bicategory. A plural equipment on K consists of a pseudo-functor asterisk from K to another bicategory M, satisfying three conditions. First, it is bijective on objects. Second, it is locally free faithful. The third condition, which is the most important, is that for every morphism F in K, the morphism F's lower asterisk has a right adjoint in M. The standard example is the plural equipment of categories. Take K as the two category of categories, cat, and M as prof, the bicategory of profunctors. A profunctor from A to B is simply a set-varied functor B of cross A, from B of cross A to set with a functor F. We associate the profunctor given by hom blank F blank like this. This is a profunctor from A to B. This assignment defines a pseudo-functor asterisk from cat to prof. Moreover, this F lower asterisk has a right adjoint given by this low F upper asterisk, and that is hom F blank, hom F blank blank. So this pseudo-functor is a plural equipment on cat. And this example encodes ordinary category theory in a two-categorical form. Let us look at the DG case. Take K as the two category of DG categories, DG cat, and let F be bimod, the bicategory of the G bimodules. Here, the G bimodule or the G perfunctor from A to B is a DG functor from B of tensor A to CDGK, like this. Given a DG functor F, we also define F lower asterisk as B blank F blank. Again, this defines a pseudofunctor asterisk from the G-cat to bimod, and it forms a pro-arrow equivalent on the G-cat. More generally, for suitable monoidal category V, we obtain a pro-arrow equivalent of V enriched categories in a similar way. Using a pro-arrow equivalent, we obtain a unified notion of limits. Let F be a morphism from J to A in the bicategory K, and let W be a morphism from J to M in the bicategory M. Then the W-weighted limit of F is defined as a morphism in K, like this, together with a right-kind extension in M, like this. We call F the diagram and W the weight. The key point is that the limit exists if and only if the right-kind extension of F lower asterisk along W exists in M, and it is representable by a morphism of K. As the name suggests, this generalizes the usual notion of limits. Let's look at some examples. For example, first consider the pro-arrow equivalent of categories. This. If we take a diagram F and choose the constant weight at the singleton set as W, then the corresponding right-kind extension is a functor of the functor taking cones over F. Its representability is exactly the usual universal property of limits, so this formal definition recovers ordinary limits. More generally, enriched weighted limits are recovered as weighted limits in the pro-arrow equivalent of enriched categories. As a simple example, consider terminal objects in the G categories. In the pro-arrow equivalent of the G categories, this takes the unique DG functor F from the empty category, and let W be the unique DG module. Then the corresponding limit is precisely a DG terminal object. In other words, it is an object A0 in A, such that for all object A, The home complexes A, A0 are zero complexes. That was a short introduction to formal category theory. Now we come to the central question of this talk. We have seen the plural equipment of the G categories. This it encodes enriched category theory of the G categories, and the limits obtained there are enriched weighted limits. However, it completely ignores the homotopy theory of the G categories. The G categories are naturally identified up to Kesai equivalence, but this equipment does not see Kesai equivalences, and the weighted limits in it are not invariant under Kesai equivalence. So the natural question is, can we construct a plural equipment that captures the homotopy theory? This is what I will discuss next. So let us now modify the bicategory of the G bimodules so that it reflects homotopy theory. Recall that in the bicategory bimod, and the bicategory of the G bimodules, the home category from A to B is the DG functor category into C DGK, like this. Instead of working with this category, we should pass to its derived category. Together with the derived tensor product of the G bimodules, this gives a new bicategory denoted by D bimod. Its home category is given by the derived category of CAB. I note that we need a cofibrancy condition to get associativity. But if the base K is a field, this is not an issue. To understand tight arrows inside the bimod, we use the following characterization. In bimod, a DG bimodule X is written as F lower asterisk for a DG functor F if and only if it is right representable. And that is for each object A, the right DGB module X blank A is isomorphic to a representable B module. Weakening this condition, we say that a DG bimodule X is right Kesa representable if for every A or every object A, the module X blank A is case isomorphic to a representable. We write DAB RQR for the full subcategory of right case representable DG bimodules and D bimod RQR for the corresponding sub-bicategory. Right case representable bimodules are often called Kessel functors because they should be regarded as a DG functors defined up to homotopy. In fact, there is a precise result proved by Towen, namely, the isomorphism classes of right Kesai representable DG bimodules, as in right-hand side, are in bijection with morphisms in the homotopy category of DG categories. Moreover, a DG factor F is a Kesai equivalence if and only if the associated Kesai factor F lower risk is an internal equivalence in the bicategory of Kesai factors D by mod RKR. So these proportions suggest that this bicategory D by mod RQR would work as a two-categorical refinement of the homotopy category of DG categories. In the non-derived situation, a DG factor has a right adjoint in bimod. A homotopical analog also holds for Kesai factors. Namely, every right Kesai representable DG bimodules or Kesai factor admits a right adjoint in D bimod. This was proved by Genovese in 2017. As a consequence, we obtain the following theorem. The inclusion of the sub-bicategory D by mod RQR into the bicategory D by mod forms a pro-alloy equivalent on D by mod RQR, which is denoted by stir in the following. So we obtain a new pro-alloy equivalent for the G categories, whose base bicategory consists of Kesai factors. Therefore, it reflects the homotopy theory of the G categories. Applying the general notion of limits in a pro-alloy equivalent to this, we obtain a notion of homotopy limits inside a DG category. I studied the behavior of these homotopy limits. Let me first explain the simplest example of a homotopy limit. Using the pro-alloy equivalent we can define a notion of homotopy terminal object or H-terminal object. Formally, it is defined as a weighted limit for suitable diagram and weight in exactly the same way as before. But we can check that such an H-terminal object is equivalent to an object A0 such that for every object A, the complex A0 is K-isomorphic to 0. Because that a DG terminal object is an object such that the home complex is isomorphic to 0. For an H-terminal object, we only require balancing up to K-isomorphism. And this is what we expect from a homotopy theoretic notion. Moreover, unlike strict DG terminal objects, H-terminal objects are preserved under Kesai equivalences. More generally, we can define other homotopy limits by choosing suitable diagrams and weights. These include H products, H shifts, and H cocoons. H shift H shift is designed to capture the degree shift of complexes, and the H cocoon is designed to capture the mapping cone of a morphism of complexes. These homotopy limits can be characterized as follows. First, at the G category, A has all H products if and only if the homotopy category H0A has products and the embedding into the derived category preserves them. Second, A has all H shifts if and only if the homotopy category H0 is closed and the shifts of the derived category. And A has all H cocoons if and only if H0A is closed and the cocoons of the derived category. Recall that the second and third conditions already appeared in the definition of a pre-triangulated category, pre-triangulated DG category. Therefore, we obtain the following reformulation. Namely, the G category A is pre-triangulated if and only if it admits the relevant homotopy limits, H shifts and H cocoons. This gives a conceptual explanation of pre-triangulatedness from the viewpoint of formal category theory. Let me mention some further properties. During to homotopy limits, we also have homotopy colimits. In particular, we have H coproducts, H coshifts, and H cones as the corresponding homotopy colimits. In fact, all colimits are built from these basic constructions. That is, the G category A admits all homotopy colimits if and only if it has H coproducts, H coshifts, and H cones. This theorem is essentially a consequence of the compact generation of derived categories. Next, let me discuss absoluteness. In a general parallel equipment, a limit or colimit is called absolute if it is preserved by any alone. By formal arguments, one can show that limits weighted by right adjoints are absolute. Ideally, colimits weighted by left adjoint are absolute. More precisely, if we are given an adjunction of weights W and V, then W-weighted colimits are equivalent to V-weighted limits, and these are absolute. This abstract statement can be applied to our homotopical setting. Let us return to the equipment star. And we can characterize which weights admit adjoints. Namely, the G bimodule X has a right adjoint in the bicategory D bimod if and only if it is right compact. This means that for each object for each object A, the DGB module X blank A is a compact object of the derived category DB. Here, an object of a triangulated category is called compact if the covariant additive Hom factor. This preserves coproducts. From this, we can see that H-terminal objects, H-shifts, and H-cocoons are weighted by light adjoints and hence absolute. And these limits are equivalent to the corresponding absolute colimits, and that is H initial objects, H coshifts, and H cones, respectively. We can also define Cauchy completeness in a plural equipment. An object A is called Cauchy complete if all left adjoint arrows with codomain A are representable by arrows. It follows formally that it is equivalent to admitting all limits weighted by light adjoints, and also equivalent to admitting all colimits weighted by left adjoints. In our homotopical equipment, we can characterize homotopy Cauchy complete. Homotopy Cauchy complete DG categories A as those for which H0A is equivalent to the full subcategory of compact objects of DA. This full subcategory, which is often denoted by path A, is the idempotent complete triangulated closure of the representables. So limits weighted by light adjoints are generated by shifts, cones, and idempotent splittings. I mentioned that a limit is absolute if it is weighted by light adjoints. However, I don't know whether the converse holds, either in general or in our setting. Let me turn to adjunctions. Genovese introduced the notion of an adjunction of Kesai functors. This simply means an adjunction inside the bicategory of Kesai functors. Of course, one can see formally that left adjoint Kesai functors preserves homotopy limits. Also, there are some results, you may expect. Given an adjunction of the G functors F and G, then the associated Kesai functors F lower asterisk and G lower asterisk also form an adjunction of Kesai functors. And every adjunction of Kesai functors F and G induces an adjunction between the corresponding homotopy categories, like this. This is because there are pseudo functors between the ambient two categories. As we have already seen, if a DG category A has H coproducts, then The homotopy category H0A has coproducts in the usual sense. In general, the converse does not hold, but under the assumption of H shifts, we obtain a reflection result. Namely, if A has H shifts, then the existence of coproducts in H0A implies that A has H coproducts. In this sense, H coproducts are reflected by the H0 construction. Since pre-triangulated DG categories have H shifts, we can combine this with the previous theorem. So we conclude that a pre-triangulated DG category A admits all homotopic limits if and only if the associated triangulated category H0A has coproducts. Using the same idea, we also obtain a reflection result for adjoints. Suppose A and B have H shifts and let F be a Kessel factor. If the induced factor H0F between the homotopy categories has a right adjoint, then F itself has a right adjoint as a Kessel factor. So far, we have obtained two parallel equipments for DG categories. One is the standard equipment coming from enriched category theory. The other is the equipment we have constructed, STAR, which captures the homotopy theory of DG categories. These two equipments are related by a comparison construction. More precisely, there exists a Lux factor, capital gamma, from bimode to d bimode, and a pseudo factor, small gamma, from dg cat to d bimode RQR. They satisfy that the following square commutes. We can see this by constructing capital gamma explicitly. And checking that its restriction along asterisk becomes a pseudo factor. In addition, the Lux factor capital gamma preserves adjunctions coming from the G functors like this form. This proposition means that the pair of gamma and small gamma behaves like a morphism between pro-arrow equipments. Moreover, this construction satisfies a universal property. That is, we can show the following. Suppose that we are given another pro-arrow equipment, Barrett, from K to M, together with a morphism from asterisk to Barrett. Concretely, this means that we are given a Lux factor, capital theta, from bimode to M, and a pseudo factor, small theta, from dg cat to K, which are compatible with the equipments, and such that capital theta preserves adjunctions coming from the G factors, like this. Moreover, assume that capital theta sends Kessel isomorphisms to invertible two cells, and small theta sends KSI equivalencies to equivalencies. Then the pair theta factors through the pair gamma like this. This theorem shows that our construction is not ad hoc, but can be characterized by a natural universal property. As an application of this theorem, we get the following. Consider the Lax monoidal functor, H0, which takes the zeroth cohomology of a complex. It is known that it induces a two-functor from the G categories to K linear categories, but it also induces a Lax functor between the corresponding bicategories of profunctors, like this. A DG bimodule X is sent to the K linear profunctor given by this composite. Then the Lux functor H bar 0 sends KSI isomorphism to cells, and the two functor H0 sends KSI equivalence to equivalence. Therefore, the pair H bar 0 and H0 factors through capital gamma and small gamma. So in particular, we have a two functor from the bimod RQR to the two category of K-linear categories. Let me finish with a few remarks. I said that the pair capital gamma and small gamma behaves like a morphism of equipments. In fact, it is an equipment morphism in the sense of verity. From what we have seen, I expect that the hot-picker pro-alloy equipment star can be characterized as the localization of the classical equipment asterisk in a suitable sense. However, at present, there does not seem to be a localization theory for pro-alloy equipment. So first we would need to develop such a theory. And also, equipments can be described as special double categories. So we may need to consider localizations of double categories. This is future work. Another question is whether we can develop a general theory over a monoidal model category. Towards such a theory, I'm now studying the cat enriched case, since cat is also a monoidal model category. It would be interesting if the resulting structure could be formulated as something like a model equipment or a model double category, but I have no idea about it. These are the differences. Thank you very much for your attention.
Thank you for your talk. Are there any questions or comments? Can I ask you a question?
Okay?
So you mentioned the notion of equipment morphism,
Yes.
and as I mentioned, the notion of plural equipment can also be formulated as suitable double categories.
Yes.
And can we characterize equipment morphisms in those double categorical terms?
I I don't I don't check yet, but it corresponds to a pseudo double functor.
Okay, I see. Okay, yeah, thank you.
Thank you.
Any other questions or comments? Yes, Richard.
Thank you for the talk. That was very interesting. So I had one small question. So at the end, you're saying some very interesting things about model equipments or something like that.
Yes.
So even without knowing that, I wonder if there are some examples that you could look at. So, for example, you could look at two categories. Sorry, monoidal categories and strict monoidal functors.
Yes.
And then that includes into an equipment which is the Kleisli bicategory for the symmetric monoidal monad on profunctors. Does that make sense? So the bicategory of generalized species.
Sorry, I don't know about species there.
So there's some papers by Nicola Gambino and Martin Hyland, and so it's Fiore, Gambino, Hyland, and Winskell. So they have papers about this bicategory. So the idea is that it kind of is in the same relationship to profunctors as monoidal categories is to just ordinary categories. So I was wondering if that might be an example. So, okay. So that's sort of like a strict. That's like the strict enrichment equipment of DG categories, and then the corresponding weak enrichment. I think it would you'd get the strong monoidal functors rather than the strict monoidal functors on in your smaller category. I'm not sure what would happen on the right. It may stay the same. I don't know. But I don't really have a clear picture of it, but I just wondered if that might be a sort of source of other examples that might help to sort of clarify what a more general theory might look like.
Thank you.
Yeah. So I mean, in general, so Steve Lack has these papers on homotopy theoretic aspects of two monads. And so I guess all I was thinking really is, I wonder if you could sort of turn those into equipment, some of those examples, and sort of get some kind of thing analogous to your picture for those situations as well.
Thank you. I check the differences.
Thank you again for the talk.
Thank you.
Any other questions or comments? If not, let's thank the speaker again.
Thank you so much.
Thank you very much, Yuki.
Thank you.